Hello students, in this video we'll see that the partial sums of the Fourier series are the best approximation in the mean to a function relative to any other trigonometric polynomial of degree n. So let's consider the space of all 2 pi periodic functions. We can even just say integrable functions to make sure all my integrals make sense. With inner product f g is 1 over 2 pi, the integral from negative pi to pi, f of theta g of theta bar d theta. And we know with this inner product that the function, the orthonormal, we have the orthonormal set, so e to the I n theta when n is in z is my orthonormal set. Okay. And so what I can do is I can write down the Fourier coefficients of the partial sums of the Fourier series. We look at S n of f of theta is just the sum over all j less than or equal to n f hat of j, where of course f hat of j is just going to be f with e to the I j theta, e to the I j theta. This of course is the nth partial sum, And we know from a previous video that these S and F's are really just Dn, the Dirichlet kernel convolution F, okay? And so what I'd like to do now is I'd like to think of this from the perspective of that this is a trigonometric polynomial degree n. So this is a trigonometric polynomial okay? And so in particular, what can I say? I can say that for any other trigonometric polynomial, for any other trigonometric, let's call that Pn of theta, which is the sum over j less than or equal to n of just some numbers alpha j e to the I j theta. That's just that's also another trigonometric polynomial degree n. So this is also a trigonometric polynomial. This is the same thing. This is also a trigonometric polynomial degree n, and just like this thing is over here, they are both trigonometric polynomials of degree n. And so now what can I say? If I consider the difference of my function and the partial sums, so notice that f minus Sn of f has no modes or no frequencies or no terms in our expansion that are between negative n and n. So this thing hat, the hat of this thing of k is equal to 0 if k is less than or equal to n, because I just cancel out all the coefficients. So in other words, what that tells me is that it says that this has no frequencies that match with these frequencies over here. So these things are perpendicular to each other. So in other words, that shows that f with f minus Sn of f is perpendicular to Pn for any of these coefficients alpha j, okay? And that's an important property because we're going to use this for show that we have the best approximation in the norm, right? So now let me consider this. Let me consider now f minus what? F minus just the sum of this polynomial over here, f minus Pn like that, okay? Well, this is equal to what? I'm going to take, this is equal to f minus Snf plus Snf minus Pn. That's just a trivial identity. But now what's the key over here? The key over here is that this thing over here, this second term over here, is a trigonometric polynomial of degree n. And this thing has no modes in between n, so these two things are perpendicular to each other. So these two vectors over here, the thing of them as vectors in my inner product space, are perpendicular to each other. These are perpendicular. Or orthogonal to each other, okay? And so what that allows me to do is it allows me to say the following. It says that by using the Pythagorean theorem, f minus Pn squared is f minus Snf squared plus this thing squared over here. Now, of course, for the square, the norm of a trigonometric polynomial is the sum of the squares, right? So it's going to be the sum, j less than or equal to n, of what? Of just f hat of j minus alpha j quantity squared. And now what's the idea? This shows that the f minus SNF norm squared, of course, what's the norm here? The norm here is we're going to put f, so in other words, what's norm squared? Norm squared, of course, is just f with f. Then in fact, the f with itself, right? And so that says that this quantity plus a positive quantity is equal to this thing. So we've just proved that what? We've just proven that f minus SNF, this thing over here is less than or equal to this thing over here. So this is less than or equal to f minus Pn. In other words, among all the trigonometric polynomials of degree n, the one that minimizes this distance over between f and this trigonometric polynomials is just the partial sums. Excellent. Now what we also have is the following. We also conclude this. We can also say that the norm of f squared is equal to f minus SNF squared plus just SNF squared, which is just the sum of the first n coefficients over here. So if we're able to show that this Sn converges to f in norm, or with respect to this inner product, or mean squared sense, our next objective is to show that we can now therefore conclude what? We can show that the sum j less than or equal to n of f hat of j squared is less than or equal to the L2 norm of f. And that's true for any n in any orthonormal set, actually. And so what this shows that this is the sum of the square of these Fourier coefficients is a convergent series, which shows that the Fourier coefficients have to tend to 0. And that's what's known as the Riemann-Lebesgue lemma. We'll spell that out in a further video. Once I can actually formally prove that this limit goes to 0 as n goes to infinity, then I'll be able to show there's actual equality between these two things. That's the Parseval theorem. So the next step is to show the mean squared convergence of the partial sums of the Fourier series to the function itself. Thank you very much.